Hi, I'm Sonja Englert. Welcome to my airplane design tutorial number 17. I talked about the airplane loads in the last video. In this one, we will use those loads to design the structure. First, I will explain two terms, stress and strain. We have to deal with different types of stress on an airplane. The simplest one is normal stress. You get this if you take a rod and pull on both ends with a force of, for example, 40 pounds. The stress in the rod is the same anywhere in the rod, and it is all in the same direction in tension. The stress in the rod is directly proportional to the force. It would be lower by 50% if you only pulled on it with 20 pounds. Normal stress is simply the force divided by the cross-section of the rod. If you would push instead, the stress would be compression, and I would have to draw the arrows the other way round. The magnitude of the stress is shown here by the length of the arrows. Typical places where you find normal stress in airplane components are wing struts, wires, and tube structures. To explain strain, we need to introduce the elastic modulus. Different materials have different elastic properties. This is a measurement of the stiffness of the material. In this sketch, I have drawn two rods from different materials. Rod 2 has a higher elastic modulus than rod 3. The two rods start out both at no load at the same length as shown in the center. If you pull on a piece of steel rod, it will deform or stretch less than a rubber rod. The stress in both rods is the same because both will have the same cross-section and the forces are the same. What is different is the strain or elongation. The strain is the stress divided by the elastic modulus. So for the same force, the higher the E modulus is, the lower is the strain. We can show this relationship also in the stress-strain curve. Material 1 has the higher E modulus. It stretches less under the same force. Material 2 is a softer, ductile material that yields before breaking. Because airplanes must not deform too much, we need to select materials with high E modulus in its construction. Normal stress is not the only kind. There are more, such as shear stress. You will be familiar with one of the applications. Every time you use scissors, you exceed the shear strength of the material you are cutting. A more airplane-related example is a beam, such as a spar that is loaded with wing shear distribution we calculated during the loads analysis. The simplest form of shear stress is calculated by dividing the shear force by the cross-section of the beam. This is also used in the second example, where a bolt is subjected to shear between two plates. But this only works if the length L is short or the thickness of the plates with a bolt is small. A spar is usually very long compared to its height, so the spar web between the caps is experiencing shear stress in a different way. The spar is carrying the bending loads from the tip to the root. If we just used a rectangular profile as the spar, it would have a normal stress distribution that looked like this. Compression at the upper end and tension at the lower side. In between, the normal stress is zero, but there the shear stress is highest. This is illustrated in this sketch. For the design of the spar, it is very important to calculate the highest normal stress at each wing station. This is done in the following way. We take the load calculated for one of the wing sections and use a preliminary estimate of the structural dimensions to check what the stress is. In this example, I use a rectangular profile as the spar cross-section because the formula for this is very simple. We calculate the area moment of inertia around the axis that the bending moment is for, in this case the x-axis. The area moment of inertia is just a function of the geometry, and it is a measure of how much the structure resists the load. You can see that the larger the height is, the larger is this number by the power of 3. This is the reason why spars need to be as high as possible to be strong, and are placed at the thickest part of the airfoil. To get the highest bending stress, we need the largest distance from the profile center of gravity to the edge of the spar, which here is Zmax. Now we can calculate the stress. If it is too high, increase the size of the material until it works. The loads that we still need to take care of is torsion. Torque on a thin-walled tube creates pure shear stress, which is what these formulas are valid for. The torsion moment of inertia quantifies the stiffness. For a round tube, its diameter and wall thickness are the only variables. The larger the enclosed area is, the lower is the shear stress and the stiffer is the structure. A tube that is fixed on one end will twist by the angle alpha when the torque is applied at the other end. Try twisting a thin-walled round tube as shown in this sketch and compare its deformation with an open profile as shown below it. The open profile will twist easily. Metal and composite wings used stressed skins for this job. A fabric skin is not counted as stressed. A single spar by itself can typically handle very little of the torque that the wing is subjected to. Because only close profiles are torsionally stiff structures, we can either add a D-section leading edge from the spar forward or use the whole airfoil cross-section by extending the skin to the trailing edge. All the structural elements and what they are needed for are shown in this sketch. You may ask why it is necessary to calculate stress. We need to do this to have an indication how far a structure is from failure. For this we use the material data at which failure happens and compare it with our structure. This gives us the margin the structure has before failure. Divide the material property, for example ultimate tensile strength, by the calculated maximum stress in a component at limit load. The result is a safety factor. This means you could increase the load 2.42 times before the part is expected to fail. As we said in the loads analysis, you normally only need a safety factor of 1.5, so this part would be okay to use as is. Some people use a slightly different definition, the margin of safety. Every material has different properties, so you have to look up the correct design allowables for what you are using, or come up with them yourself by testing samples to destruction. If this was all there was to it, structural analysis would be pretty simple. Unfortunately, it isn't. I will give you some more examples. If you push on the ends of the rod instead of pulling, the failure mode may shift from tearing apart from tension to buckling and compression if the rod is long enough. The stress at which tearing or buckling happens is unlikely to be the same. When fasteners such as bolts or rivets are used, in addition to checking the tensile or shear strength of the fastener, we also need to calculate the bearing stress in the parts that are joined. The bearing stress depends on the shear load, the fastener diameter, and the sheet thickness. If the bearing stress is too high, you can increase the thickness, the bolt diameter, or use more bolts. The bearing stress allowables depend on the material of the sheet and are valid only for a certain minimum edge distance of the hole. If the load is too high, the hole will become elongated and the material will eventually tear out. After the structural analysis for the airplane is completed and the airplane was built, the results need to be checked by test. It is not possible to account for all the factors and combination of loads on the structure, including fabrication tolerances and other errors. To make sure the structure does not fail in flight, the primary structure is loaded in a ground test. This may be as simple as stacking sandbags on the wings. The wing here is inverted because the highest flight load is up, but gravity pulls down. A support that simulates the fuselage is used to carry the whole assembly. This works only for short wings that do not bend much under load, otherwise the weights will slide off. The alternative is to use a wiffle tree with an actuator to apply the bending, shear, and torsion as in this picture. It is not necessary to test both wings together if they are joined in the center. A substitute structure can be used to keep the other side shorter. The fuselage is tested by applying forces to the engine mount and tail structure while it is supported at the wing attach points. For a prototype, it may be acceptable to load the structure to limit load only in order to prevent potential damage at ultimate load. Otherwise, a dedicated structural test article is used to test to ultimate load or failure. With this, I am concluding this video and my tutorials on airplane design. I hope you have enjoyed them and have learned something. Good luck with your project.